Hi, I'm Jack McGrath. I'll be talking about generating three-component velocity fields for Central South Island of New Zealand from S1 InSAR. So South Island is the surface expression of the transpressional part of the boundary between the Pacific and the Australian plates, where approximately 40 millimeters per year of plate motion is partitioned onto the Alpine fault as 37 millimeters per year of dextral strike slip and about 10 millimeters per year of convergence. The horizontal component of this velocity field is well constrained by a dense GPS network with a spacing of approximately 5 to 20 kilometers. However, there's little in the way of vertical geodetic data, with the exception of a fault normal vertical GNSS transect along the Roseroa River here, which indicated uplift rates of up to 5 millimeters per year focused 20 to 30 kilometers away from the fault, with further geological evidence indicating that peak displacement is focused further to the north and decreasing along strike from a maximum of 8 to 12 millimeters per year dip slip. Therefore, what we're going to do is we're going to use four InSAR tracks from Sentinel-1 that cover the Central South Island, taking advantage of the fact that most of this region is in fact covered now by at least 3 InSAR tracks, with the area of highest uplift being covered potentially by up to 4 InSAR tracks. So when we're doing this work, we use a stamped processor, which unfortunately prevents us from using a simple N/M interferogram network, as the stamps requires a pixel to be coherent throughout all interferograms, and there's a strong seasonal control on coherence of pixels, particularly near to the fault due to snow cover. Therefore, instead we're going to use a seasonally variable network where we create dense networks of interferograms over coherent summer months and then connect these networks together using a few coherent long baseline interferograms. And we're going to prioritize interferograms that are coherent in a region adjacent to the fault, approximately the size of one burst, that appears in all 4 different tracks. So the way we do this is by we initially make a combination, and we make every combination of interferograms from all the acquired epochs before weeding out any interferogram with a mean coherence less than a threshold of 0.15. We then carry out an inspection to ensure that all interferograms are connected to the network, identify any isolated subsets, and we remove these from our network. And this results in a seasonally variable small baseline network of dense summer months connected by potentially multi-year coherent interferograms. As I said, the line of sight velocities are then generated using stamps with a linear tropospheric correction applied. The northeastern portion of track 125A is masked out due to it containing a lot of contamination from the Kaikoura earthquake in 2016, although largely this doesn't extend into our study area, so it's no longer considered after that. Each line of sight velocity field is then reprojected onto a common 1 kilometer UTM grid. We reference it to an Australian fixed plate velocity, so they're all in the common reference, and then we remove the north component from all the LOS fields by taking out the local north GPS field. Any pixel then with at least 3 or 4 associated line of sight velocities are then inverted for their east and their vertical velocities. So inverted uplift rates show that we have the maximum uplift rates are found further north than the GPS transect, but also focused approximately 20 kilometers off from the fault, reaching a maximum of about 12.2 plus or minus 1.3 millimeters per year in this region. And again, from this peak uplift, this decreases along strike. The overall trend of our uplift rates not only matches the trend of that measured from the GNSS, but it's also very similar to that of an exhumation profile derived from thermochronology and seismicity. The east component of the velocity showed very little along strike variation. However, we can combine this east velocity and the north component that we removed to resolve the fault parallel and the fault perpendicular components. By then carrying out a Bayesian inversion of these velocities along the profile using a vertical screw dislocation model, we get a slip rate of 36.5 millimeters per year on a fault dipping at 63 degrees and locked at 15 kilometer depths. This slip rate As the slip rate matches the far-field motion, though is higher than the geologically measured and geodetically modelled slip rates of about 28 millimetres per year on the fault, which is lower than the overall plate motion due to internal deformation of the Southern Alps. The fault dip matches that has been measured at the surface, and the locking depth is also falling within the 13 to 18 kilometre range, which has been derived from modelling of the vertical GNSS datasets.